Most people look at an offshore wind turbine and see the blades, but the real engineering structure starts far below them. Before that tower can rise above the ocean, engineers have to manufacture a steel foundation longer than a football field, heavy enough to challenge the largest transport ships, and precise enough to survive decades of waves, storms, corrosion, and shifting seabed. It's more than a steel tube. What sits beneath decides how long it can keep operating at sea. When people picture offshore wind, they picture this. At the Greater Gabbard site, a jack-up vessel plants its legs on the seabed and lifts itself above the waves to serve as a stable crane platform. Tower sections rise into the sky. The nacelle is hoisted to the top. Each blade is bolted on with millimeter tolerance under heavy offshore winds. From the coast, all you see is a row of clean white towers spinning above the sea. The whole image of offshore wind lives in that one frame. But the frame is missing the most important piece. The structure carrying all of that weight usually stays far below where most people ever look. In the German Bight, 67 XXL monopile foundations carry 6 megawatt turbines that power 400,000 homes. Each monopile is up to 85 meters long, 7.8 meters in diameter, and weighs up to 1,300 tons. They are upended, driven into the seabed with hydro sound dampers and a double bubble curtain, then capped with a transition piece using bolted and grouted connections. Once the sea closes over them, they are rarely seen again after installation. Here is why that hidden column matters more than the turbine on top of it. The turbine above the waterline can be replaced. The foundation is far more difficult to replace. It has to absorb the full weight of the turbine, the bending force of the wind on every blade, the constant pounding of waves, underwater currents, vibration, and salt corrosion for decades. 2 turbines can be installed in 4 days. The foundation has to last 40 years. And the loads keep getting heavier every year. A record-setting rotor blade is built in one piece, 75 meters long. The largest fiberglass component ever made. No seams, no splices. Hauled by truck at nearly 100 meters total length, it pairs with a 6 megawatt turbine. Bigger rotors capture more wind, but every extra meter of blade transfers more force straight down into the foundation. Now scale that problem up to 8 megawatts. An 8 megawatt offshore turbine enters full load operation, featuring black start technology that lets it restart without external power. The launch signals readiness for bulk orders in the 8 megawatt class. But more power above the water means more weight, more vibration, more torque, and the monopile below has to absorb every bit of it for the entire life of the project. Not every foundation is buried in the seabed. Off the coast of Scotland, 5 6-megawatt turbines sit on floating spar substructures over 90 meters long, around 14.4 meters at the widest diameter, weighing roughly 3,500 tons each. They are held by suction anchors, 5 meters wide, 16 meters tall, and 111 tons apiece. A different floating concept proves the same point from another angle. Off Aberdeen, the Kincardine project installs the North Sea's first semi-submersible floating wind turbine. The platform is fully assembled at the quayside, then towed to a pre-installed mooring system where 4 anchors wait. What people see above water is only a fraction of the engineering mass required below it. Closer to shore, the foundation problem changes form again. Off the coast of Bac Lieu in Vietnam, near-shore turbines stand on reinforced concrete pile foundations cast directly at sea. Barges, heavy-lift cranes, and floating concrete pumps build circular and polygonal pile caps supported by a purpose-built 10,000-ton barge launched just for the project. Whatever the depth, the rule stays the same. The visible turbine is only the tip. An important offshore wind principle. Turbines only become possible after marine foundations, transport systems, and heavy construction networks create a stable industrial base capable of surviving waves, saltwater exposure, and continuous environmental loading. And every one of these offshore foundations has a long journey before it even reaches the sea. Modern monopiles can stretch more than 100 meters and weigh thousands of tons. Tripod foundations weigh hundreds. Moving them is its own engineering problem. At the quayside, each vehicle coordinates with heavy-lift cranes and specialized vessels for loadout. The foundation has to survive the road before it ever survives the sea. But before this structure can be driven into the seabed, it has to begin as something much simpler, a flat steel plate. And turning that flat plate into a foundation longer than a building is where the manufacturing challenge begins. Long before the foundation gets lifted, flat steel has to be forced into a perfect cylinder, and at this size, even a small distortion gets expensive fast. Offshore foundations begin as enormous steel plates up to 150 millimeters thick, stiffer than anything found in regular construction. Inside heavy fabrication halls, rolling machines gradually curve the steel into giant cylindrical sections, with hydraulic pressure measured in thousands of tons. Submerged arc welding then locks the shape permanently, fusing the seam from both sides in long, controlled passes. Precision matters immediately because these structures may eventually stand 94 meters tall, weigh 2,200 tons, and operate for decades under wave loads, corrosion, vibration, and constant offshore stress conditions, with offshore repairs becoming extremely difficult once they are installed at sea. Inside that fabrication line is the machine handling one of the most difficult steps, turning a flat slab of steel into a curved cylinder. A 3-roll plate roller with variable geometry handles plates up to 4,200 millimeters wide and 240 millimeters thick, designed for monopiles, transition pieces, jackets, and tripods. A CNC system with a camera lets a single operator hold tight roundness tolerances around the clock. When monopile diameters reach XXL territory, 3 rolls are no longer enough. A 4-roll plate bending system built specifically for XXL monopile and offshore foundation production handles plates up to 4,200 millimeters wide and 180 millimeters thick, with pre-bending up to 160 millimeters. The machine is fed by a wind tower automation line with a feeding table, top and side supports, and a clamping system for onboard tack welding, all controlled through CNC. A rigid structural frame and electronic roll balancing system are engineered to deliver accurate roundness on every can, with a short flat part at the plate edges so welding alignment stays clean. High pre-bending force shapes the edges before full rolling begins. Automatic calibration cuts cycle time. Micro-positioning allows fine adjustment. For offshore foundations, this level of repeatability is what separates a usable cylinder from an expensive piece of scrap. The scale of what these machines can roll is hard to picture until you see one in operation. Inside a large fabrication hall, a 4-roll bending machine with upper and side supports rolls steel into diameters of up to 15 meters with a load capacity of 150 tons. Inside the workshop, finished cans line up in long rows along the floor, while overhead cranes move plates between the feeding table and the rolls. The same principle drives plate rolling lines across the offshore wind industry, even when the final product is a different shape. At a Portuguese facility, plates are first cut and beveled by CNC to prepare the weld groove, then fed into a 4-roll plate bending machine that forms each can with consistent roundness. Longitudinal and circumferential welds are completed using submerged arc welding, and laser alignment tools verify circularity after each pass. The finished cans are then joined into jacket-type substructures inside a dry dock before being towed out for installation. As cans get larger and wall thickness grows, the rolling line itself becomes more like an automated factory than a single machine. A fully automated 4-roll plate roll, available in linear or planetary versions, comes paired with a wind tower automation system that brings together a motorized feeding table, an aligning system that positions plates for both cylinders and cones, a tiltable vertical support that holds the can during rolling so it does not collapse, lateral supports that prevent the can from springing back open, and a clamping system for onboard tack welding. As cans get larger and wall thickness grows, the rolling line itself becomes more like an automated factory than a single machine. A fully automated 4-roll plate roll, available in linear or planetary versions, comes paired with a wind tower automation system that brings together a motorized feeding table, an aligning system that positions plates for both cylinders and cones, a tiltable vertical support that holds the can during rolling so it does not collapse, lateral supports that prevent the can from springing back open, and a clamping system for onboard tack welding. The full line runs through CNC control. Rolling speed reaches up to 7 meters per minute, with simultaneous movements to cut total cycle time. Tack welding can start on one can while the next plate is already being rolled. The operator has very little to do beyond supervising. Precision sits at the heart of the system. Once each can has been rolled, the real assembly of a monopile begins. Engineers first prepare detailed drawings that define every dimension for each pile. Steel plates are delivered by water, unloaded, and surface treated before entering the line. Each plate is rolled into a cylindrical section, then tack welded to hold its shape. Longitudinal welding seals each can, with internal welding, external grinding, and external welding to guarantee strength. The finished cans and conical sections are then shipped by barge to a larger assembly hall, where they are joined by circumferential welds into a full monopile. Ultrasonic inspection, optical checks, and dimensional measurement follow, then protective coating, outdoor storage, and final loadout onto installation vessels. Not every section of a monopile is a perfect cylinder. Some segments taper from one diameter into another, and that brings a different rolling problem. Cone forming on a 4-roll plate roll begins by pinching the plate between the rollers, keeping the minor diameter side slightly looser than the major diameter side. The side roller is tilted, and the first edge is pre-bent. After checking both radii against templates, the plate is flipped and the second edge is pre-bent. Finally, both side rolls are raised to equal positions, and rolling continues until the final conic shape forms. Forming a cone at large diameter is one of the most delicate operations in the whole pipeline. A cone-stopping attachment slows the plate on the minor diameter side, forcing the steel to fan around the rolls. The side rolls are tilted at an angle matching the cone slope rather than raised in parallel. Forming happens across multiple passes, with the operator constantly checking that the two edges will close cleanly when the cone meets itself. By this point, every piece of the puzzle has come into view. A flat steel plate, thick enough to stop a bullet, becomes a curved can under thousands of tons of hydraulic force. Cans become tubes through long, deep welds. Tubes become sections. Sections become a single steel column long enough to lie down across a football field. Whether the final product is a monopile sunk into the seabed or a wind tower standing above it, the same factory logic runs underneath. Roll, weld, inspect, coat, repeat, at a scale where every millimeter of error multiplies into a problem worth tons of steel. And once the cylinder finally exists, the real engineering question shifts. Because a tube, no matter how perfect, is still not a foundation. It still needs interfaces, flanges, platforms, ladders, boat landings, cable entries, and a transition piece that can connect the steel below the water to the visible turbine above it. The transition piece may look like just another steel section, but it is the section crews interact with every day once the turbine begins operating offshore. Large steel plates are rolled into cylinders, welded, checked, and assembled with ladders, platforms, cable entries, and alignment details that allow the future tower to connect accurately offshore. Secondary steel components are fabricated alongside the main shell, so maintenance crews can later access the structure safely at sea. Multiple coating layers are applied because saltwater exposure continuously attacks exposed steel surfaces. After painting, electrical and mechanical equipment is installed before final inspection. The production flow resembles a heavy industrial assembly line, with several transition pieces progressing simultaneously through fabrication halls before shipment toward offshore wind installation sites. Once the transition piece is built, the question becomes how it actually fuses with the steel below. The same offshore fabrication logic that produces transition pieces also appears in much larger jacket structures used in the broader offshore industry, and that logic centers on one critical concept: grouted nodes. At the Mariner offshore field, located in water depths between 97 and 112 meters, around 130 kilometers off the British coast, an 8-legged launch jacket was fabricated as the structural backbone of the project. The jacket itself weighs 22,400 tons, with a roll-up weight of 4,500 tons, and it is engineered to support more than 50,000 tons of topside structure. Weld repair rates stayed remarkably low at 0.6%. Among its key innovations are grouted nodes, connection points where cement-based grout is pumped into the gap between steel members, then allowed to cure into a permanent load-bearing joint. The same principle of grouted connections is exactly what links a transition piece to a monopile in offshore wind, sealing the steel into one continuous structural assembly. To picture how that grouted connection ends up underwater, it helps to watch a jacket actually arrive at sea. This example comes from the oil and gas industry rather than offshore wind, but the same offshore fabrication and heavy lift logic is used across both sectors. A heavy derrick vessel transports and installs giant offshore steel structures weighing thousands of tons. What looks slow from a distance is actually a tightly calculated sequence where balance, sea motion, and lifting stress are monitored constantly. In this operation, a 2,000-ton jacket slides directly from the barge into the water before a separate 1,500-ton topside is lifted into position. The vessel's main crane can handle up to 4,400 metric tons, allowing massive offshore assemblies to be positioned with controlled precision, even in difficult marine conditions. By this stage, even a small alignment error can delay an offshore project worth millions. When monopile is no longer the right answer, the foundation becomes a jacket, and the entire installation sequence changes. Jacket foundations are often used when water depth, seabed conditions, or structural loads make a single monopile less practical. For an offshore wind farm in Scotland, foundation steel is shipped, then carried to site by a heavy lift crane vessel. The installation begins not with the jacket itself, but with a massive pile installation frame, a template lowered to the seabed first, with 4 independently adjustable legs and mud mats to keep it perfectly level. Remote-operated vehicles monitor the alignment underwater. Each pile is lifted vertically, lowered through the jacket guides, and driven deep into the seabed by a massive hydraulic hammer. After driving, each pile is measured precisely, so the incoming jacket structure will lock onto it without misalignment later. Once the piles are in place, the jacket itself can finally come down to meet them. A heavy lift crane vessel lowers the bright yellow jacket structure onto pre-driven seabed piles. Long steel piles are then guided through the sleeves at the corners of the jacket and driven deeper into the ground by hydraulic hammers, monitored continuously from a control room. After driving, grout is pumped into the gap between each pile and its surrounding jacket sleeve, creating a permanent, load-bearing bond between foundation and structure. This is where the real connection is made. 2 pieces of engineering most people never hear about: the pile gripper and the grout seal turn a temporary alignment into a permanent foundation. Jacket pile grippers are custom-built mechanical rings fitted with hydraulic pistons. After a jacket is lowered into position, its legs slide down over the pre-driven seabed piles. The grippers then activate, clamping the jacket onto each pile from inside, holding the entire structure stable while waves, currents, and wind try to move it. Without that grip, leveling the jacket in real offshore weather would be nearly impossible. Once the structure is locked in place, the grout seal does the second half of the job. Manufactured as a unique dual-lip sealing assembly, it sits at the bottom of the jacket sleeve and prevents the cement grout from escaping into the sea while it is being pumped into the annulus, the gap between the pile and the jacket leg. Grout seals are produced in diameters ranging from 600 millimeters all the way up to 3,650 millimeters, sized to match the foundation in question. Many also include a mud wiper at the bottom, which keeps seabed sediment from pushing up into the grout zone. Once the grout is pumped in and cures, the temporary mechanical connection becomes a permanent structural one. The jacket and the piles are now a single load-bearing system, ready to carry the turbine, transformer station, or platform above it for the entire life of the project. From the first steel cut to the final grouted connection offshore, the same fabrication and heavy lift process drives every giant jacket structure, whether it supports offshore energy production or a wind turbine standing far out at sea. Although this project supports a gas platform rather than a turbine, the offshore fabrication logic shown here is the same kind used to build large jacket foundations in offshore wind. The project begins with FEED, front-end engineering and design, where every node, brace, and tubular connection is calculated to survive North Sea conditions for decades. Fabrication takes place at a yard in Vlissingen, the Netherlands. Tubular sections are welded together into a vast three-dimensional steel frame, weighing roughly 9,150 tons, with cranes lifting and rotating multi-thousand-ton subassemblies during construction. Once complete, the jacket is skidded, pushed by hydraulic jacks, onto a transport barge in a controlled loadout, then towed from the Netherlands all the way to the Valemon field in the Norwegian Sea. Offshore, one of the largest crane vessels in the world lifts the jacket off the barge and lowers it onto the seabed with millimeter-level precision. Long foundation piles are driven through the legs of the jacket, deep into the ground beneath. Grouting follows, locking the piles to the jacket structure permanently. Finally, the topside module is lifted into place. Every stage, engineering, welding, skidding, lifting, piling, grouting, exists in offshore wind jacket projects too. Transition pieces and jacket foundations rely on far more than large steel diameter alone. Their strength also depends on extremely precise tubular connections. This cutting process demonstrates how CNC-controlled systems prepare offshore pipes up to 4,500 millimeters in diameter, with wall thicknesses reaching 120 millimeters. Mobile cutting equipment is installed directly around giant tubular sections, while rotators slowly turn the pipe during automated thermal cutting. Engineers use 3D CAD data to generate bevel geometries such as K, X, V, and Y preparations that later support high-strength welded joints offshore. Dry runs verify cutting accuracy before thermal cutting begins, reducing costly rework during fabrication. Although the example focuses on offshore jacket legs, the same preparation logic supports many offshore wind structures where precise fit-up quality affects alignment, welding performance, fatigue resistance, and the long-term reliability of transition piece and jacket connections. One of the most demanding steps in that chain is also one of the most overlooked: moving the finished jacket from land to barge. At a fabrication yard in Vlissingen, a complete jacket is skidded out of the assembly hall using a self-propelled modular transporter system, hundreds of synchronized wheels carrying thousands of tons of steel toward the quay. A dedicated transport barge waits alongside, with its ballast pumps continuously adjusting water levels to keep the deck perfectly level as the enormous structure rolls aboard. Engineers monitor every movement. Once loadout is complete, the entire offshore assembly sequence begins again. This project follows both jacket fabrication and offshore installation using methods similar to those seen in large offshore wind structures. The topside and jacket are fabricated separately before each structure is transported by barge toward the offshore field. Offshore cranes then lower the jacket into position while piles secure it into the seabed. After the foundation stabilizes, the topside is lifted and aligned carefully onto the jacket structure above. The sequence demonstrates why offshore foundations require more than strength alone. Every lifting phase depends on accurate geometry, controlled motion, and carefully prepared connection points. While this installation supports offshore energy production rather than a turbine tower directly, the same offshore assembly logic appears in jacket-based wind foundation systems operating in deeper marine environments. Some offshore foundations are so large they are no longer jackets or monopiles at all. They are floating steel structures held in place by their own mass and mooring system. Although this project supports a gas field rather than a wind turbine, it shows how far the offshore industry can push fabrication scale. The spar substructure weighs about 46,000 tons, measures roughly 200 meters long, and operates in water depths near 1,300 meters. Massive sections are fabricated as megablocks before final offshore assembly and transport. The farther offshore projects move, the more installation precision and structural coordination begin to dominate the entire construction process. Once the steel is rolled, welded, fitted, and protected, the factory challenge ends. But the offshore challenge is just beginning, because now these enormous parts have to be moved from land to sea without damaging the precision built into them. Before offshore foundations leave the yard, engineers already know corrosion control will become a decades-long maintenance problem rather than a single manufacturing step. Large offshore foundations rely on carefully formed connection edges before coating systems are applied. This flange-forming footage shows heavy rollers shaping thick steel edges into controlled circular profiles suitable for joining large cylindrical sections. Operators continuously adjust hydraulic pressure, rotation speed, and roller alignment while checking for cracking or uneven thickness. Precise geometry matters because flange areas later support bolted interfaces, coating transitions, sealing systems, and secondary steel attachments exposed to seawater spray. Even small forming defects can create stress concentrations where corrosion begins earlier. The process also demonstrates how large offshore components receive smooth surfaces before blasting, painting, and long-term protection systems are added for marine surface. Wherever the foundation changes diameter, the geometry itself becomes a corrosion problem. This forming system handles cold forming up to 80 millimeters thick and hot forming up to 200 millimeters, producing smooth, large-diameter curved sections with tight tolerances. Accurate edge geometry helps create reliable welded joints and coating transitions on offshore structures. In corrosive marine environments, coating failure often starts around irregular welds, sharp corners, or damaged surfaces where salt water remains trapped. Manufacturing processes therefore focus not only on strength, but also on preparing surfaces for blasting, metallizing, primer layers, and final protective coatings. The ocean attacks slowly, so durability depends heavily on careful forming and finishing before installation ever begins offshore. This highlights the scale and precision required when forming thick steel edges for large offshore structures. A flanging machine shapes the edge of a 4.5-meter circular plate, rotating it through pressure rollers until the inside diameter is reduced to 4.3 meters. The finished circumference reaches 13,502 millimeters, with minimum plate thickness measured at 36.6 millimeters after forming. Uneven forming can damage coating adhesion or create small pockets where seawater and oxygen remain trapped. Splash zone areas are especially demanding because repeated wet and dry exposure accelerates corrosion faster than continuously submerged sections. Forming these massive curved heads takes machinery built specifically for the scale of offshore work. A portal frame press of 1,000 tons capacity handles cold blanks up to 9,100 millimeters in diameter and 90 millimeters in thickness, within a lifting limit of 27 metric tons, with a CNC manipulator for full automation. The press produces heads with smooth surfaces and a regular spherical profile, and surface smoothness directly affects corrosion life because every microscopic pit or roughness becomes a future starting point for rust under wet-dry cycling. The high-speed playback system allows exact, uninterrupted repetition of forming sequences, ensuring that every head in a production series matches the same protective geometry. Not all offshore steel is tubular. Much of the secondary steel, ladders, brackets, platform supports, is shaped from profile sections. This profile bending system shapes heavy structural sections into controlled curves for large industrial assemblies. Although smaller than monopiles, these components often sit in the atmospheric and splash zones where corrosion exposure becomes extremely aggressive. Access platforms and external frames receive repeated salt spray, wave impact, and oxygen-rich moisture every day offshore. That is why coating systems extend beyond the primary foundation shell to nearly every exposed steel surface. The flange connection is where the ocean starts looking for a way in, which is why some of the most aggressive corrosion protection on the entire foundation is concentrated around these steel interfaces. Forged flange production begins with heated steel billets shaped under massive presses before ring rolling, heat treatment, machining, and inspection. These processes improve strength, toughness, and dimensional stability while preparing surfaces for corrosion protection. Offshore structures commonly use coatings, galvanizing, cathodic protection systems, and corrosion allowances together rather than relying on one barrier alone. Sacrificial galvanic anodes slowly corrode themselves to reduce electrochemical damage on the main steel structure, especially in submerged zones. Engineers also inspect flange faces and bolt connections carefully because trapped moisture can accelerate localized corrosion. Long service life offshore depends on manufacturing accuracy as much as heavy structural strength and large dimensions. Inside the flange factory, seawater protection starts while the steel is still being built. Steel bars are cut to specified sizes, then forged. At full production scale, the same corrosion control approach keeps moving across long rows of flanges, rolled rings, and forged components every single month. Inside a forging plant in Dingxiang, Shaanxi, a region known for heavy forging, steel billets are heated in industrial furnaces until they glow red, then placed under massive hydraulic presses or steam hammers to be shaped through free forging. These same forged rings and flanges become the structural connection points and corrosion fronts on offshore foundations, where every coated millimeter has to survive decades of salt, oxygen, and tidal cycling. What leaves the forge as glowing steel will eventually spend its working life surrounded by seawater and constant vibration offshore. But even a perfectly coated foundation still has no value until it is placed into the seabed, and that step changes the problem from manufacturing to offshore execution. Before a monopile ever reaches the sea, another challenge appears first: building the lifting system capable of moving parts too heavy for ordinary ports and cranes. At Bremerhaven, one of the most powerful conventional cranes installs 4 platform legs on a wind turbine installation vessel, each leg 87 meters long and 920 tons in weight, lifted with 132 meters of boom reach. Behind every successful offshore lift sits a generation of cranes built specifically for loads no other equipment can handle. Modern ring cranes can be assembled in sections, shipped worldwide, and configured for difficult industrial environments. Their long boom systems allow operators to rotate and lower offshore components with careful control while maintaining balance through massive counterweight arrangements. For offshore wind installation, that precision matters because monopiles, transition pieces, and jackets cannot tolerate uncontrolled movement during lifting. Some crane vessels are built for one purpose: to install foundations and turbines that no other vessel in the world can. A 3,000 metric ton offshore mast crane is installed, commissioned, and tested on a crane vessel within 27 days. The vessel itself was converted from a semi-submersible heavy lift vessel into a self-propelled crane vessel, with its primary focus on the installation of jackets, monopiles, and offshore wind turbines, the exact components that define offshore wind foundation work. Not every wind turbine installation happens from a vessel. Onshore and nearshore turbines rely on equally massive crawler cranes assembled piece by piece on land. A 650-ton crawler crane, designed for heavy lifting tasks including wind turbine installation, is assembled on-site in stages. The track frame and turntable are connected first. The luffing boom jib is built up section by section, then attached to the main body. Large individual crawler tracks are hoisted into position and mounted. The operator's cabin and counterweight platforms are installed afterward. Red lattice sections are joined together to form the long main boom, which determines how high and far the crane can reach. Steel cables are threaded through pulleys, and the heavy-duty hook block is attached at the end. By the time everything is rigged, the fully assembled crane stands at tremendous height, ready to lift nacelles, blades, and tower sections into position. Once the cranes are in place, attention shifts to the machine that completes the foundation itself, the hydraulic hammer that drives the monopile deep into the seabed. An XXL hammer, reported as one of the largest in the world, is shipped from Hamburg to Flushing on a heavy lift vessel with a total lift capacity of 1,400 tons safe working load. The hammer itself weighs 609 tons, measuring around 7.75 meters wide and 24.5 meters tall. Loading begins with a 6.5-meter anvil installed inside a 257-ton pile sleeve. Then the hammer is upended on top, secured by 90 screws. The hammer will be used to drive monopiles for the Kriegers Flak offshore wind farm project. Some pile driving systems become so large that they must be shipped in sections and assembled close to the project site. The Octokong vibratory hammer was transported internationally before final assembly near a major bridge construction zone. Although this footage comes from civil marine infrastructure rather than offshore wind, the same foundation logic appears in offshore installation work. Large marine piles require coordinated lifting, hydraulic power systems, transport barges, and careful offshore handling before any driving operation begins. Assembly teams check alignment continuously because vibration equipment transfers huge forces directly into steel structures during foundation installation across difficult marine environments and changing sea conditions. Seeing one of these hammers in action makes the scale of pile driving energy visible. The Octokong vibratory hammer was used to install steel piles for a bridge project, with each pile measuring 22 meters in diameter and 40 meters in length, weighing approximately 450 tons. The hammer delivers a driver force of 40,000 kilonewtons at a power output of 7,158 kilowatts. The pile is lifted from a barge by an offshore crane, positioned in the water, and the hammer is then lowered onto its top to vibrate it into the seabed. Offshore pile driving is never a single operation. It is a continuous logistics chain of equipment, vessels, and people working around the clock. For one major offshore bridge project, 4 large piling rigs were mobilized to install 325 piles across 32 piers. It demonstrates the same offshore execution pressures found during monopile and jacket installation. Even on land, pile driving follows the same fundamentals, and watching it close up makes the offshore version easier to picture. Pre-stressed, high-strength concrete piles are produced in a sequence that begins with cutting and heading steel bars, coiling wire into a reinforcement cage, assembling the cage inside a steel case, and pouring high-strength concrete into the mold. Bolts are tightened, steel bars are tensioned, and the assembly undergoes rotary molding for around 11 minutes. Steam curing follows for roughly 12 hours, after which the case is removed and the finished pile is ready. Pile driving then begins on site, with a hammer striking the top of each pile to drive it into the soil, closely monitored for depth and alignment by engineers. And finally, what every offshore foundation requires, what the entire industry depends on, is precision at scale. Drilling rigs install segmental casings vertically into the ground, position cages or H-beams inside, and pour concrete to form interlocking pile walls. The same vertical alignment logic that holds these onshore casings perfectly straight is what every offshore monopile crew demands at sea. Once the foundation is locked into the seabed, the wind farm is still just steel standing in salt water. What turns it into a working energy system is everything that comes next, and the first piece of that everything is cable. At the Gemini Offshore Wind Park, specialized cable installation vessels lay submarine power cables across the seabed, link each turbine foundation, and then bury the cables for protection. Without this stage, the foundations carry no electricity, and the wind farm produces nothing. Inside the wind farm itself, the turbines are connected by a network most viewers never see, the inner array grid. During the Nordsee 1 project, 59 submarine cables totaling 68 kilometers were installed between foundations across the wind farm. Specialized vessels handled pull-in, termination, testing, and seabed laying operations, while ROV systems monitored touchdown positions underwater. Messenger wires guided cable ends into each turbine foundation before trenching equipment buried the lines approximately 1.5 meters below the seabed for protection. Rock berms and mattresses secured crossings where routes intersected other infrastructure. Every cable section required tension monitoring because excessive bending or seabed movement could shorten service life. Without these buried electrical connections, even fully installed turbines would sit out at sea without ever feeding power to shore. Long before a cable ever touches the sea, it spends months being built. Submarine power cables for offshore wind farms are not assembled in days. One major manufacturing and delivery sequence was filmed over 6 months, covering the conductor stranding, insulation, armoring, lead sheathing, testing, and final loadout onto the cable vessel that will carry it to the offshore installation site. Some installation problems cannot be solved by a normal cable vessel. The water is simply too shallow. For this project in the United Kingdom, the export cable had to reach across Morecambe Bay, an area of vast tidal flats where conventional vessel access becomes impossible at low tide. The solution was an engineered grounding. The cable-lay vessel was deliberately positioned, then allowed to settle onto the sand as the tide retreated, leaving the hull resting on the seabed. From that grounded position, the vessel coordinated directly with onshore teams. Excavators guided the cable from the ship into pre-prepared trenches on land. Roller systems and cable guides protected the cable as it crossed the tidal flat. The vessel's onboard cable carousel released the line continuously, working across multiple tidal cycles. By the end, the most impressive part of the turbine is no longer the blade. It is the steel system below the waterline, the monopile, the transition piece, the grouted connection, the buried cable that allows the blade to exist in the first place. After seeing the complexity behind it, do you think offshore wind is a necessary step forward or a system too complex and expensive to maintain at sea? Thanks for watching. If you enjoy seeing how massive industrial systems are designed, built, and pushed to their limits, stay with us for the next one.